Hello everyone, so this is going to be a video about Argand diagrams. It's really just because one guy asked, I might have made this video anyway, but one guy asked, here he is. Thank you very much for commenting. So he asked, he was curious, why does this make sense? Okay, we're talking about this relation over here, e to the I theta equals cosine of theta plus I sine theta. Why does this make sense? Why is there a relation between trigonometric functions and non-trigonometric functions and etc.? So I thought I'll try to deliver my best explanation. There's not really, it's kind of just how nature works, to be honest, but I'll try to deliver an explanation. So the first thing you need to understand is what an Argand diagram is. And let's just get a little bit of intuition for it. So let's say right here, this is my number line. Ignore the imaginary axis, just look at the real axis. This is all the numbers that we use. 1, pi is on there, all the numbers are on there. Okay, so you got 1, you got 2, you got so on and so forth, and then also you got the negative direction over here. That's 0, and negative 2. Okay, all the numbers that we use, we know and love, are on this diagram. Oh, not this diagram, this number line. Okay, now let's consider the fact that I squared is equal to negative 1. All right, so let's say we start at 1, okay, and we multiply by I squared. Well, that's going to give me negative 1. Makes sense, right? 1 times negative 1 is negative 1. And by the way, this is just something we're going to use. It's something we invented. It's just the way it is. Okay, we thought, let's think of a number that when we square it equals negative 1. Because that kind of number doesn't exist on this axis. But if we square it, it does exist. So what we can do is we can think about, okay, I'm here, and I somehow end up over here. So maybe I must have done some sort of rotation, 180-degree rotation to end up there. Okay, if I'm timesing by I squared. And then we can do that again. We can go negative 1, okay, and then we can times by I squared, and we will end up back at 1, because negative 1, I squared is negative 1, times negative 1 is going to give me positive 1. Okay, so again, I'm going to over here, and then I end up over here. So it's another 180-degree rotation. I know my circle isn't perfect, but hopefully you get the idea. Okay, so we times by I squared. What happens if we just times by I? Well, I did say that I isn't a real number. It doesn't exist on this axis, which means it must exist somewhere else. And if it exists somewhere else, the best real sort of thing to think about for the 1 times I must be, which is I, must be halfway in between, right? So if it's 180, 180 divided by 2 gives you 90. So it must be 90 degrees away, and that's just kind of the intuitive approach. And then again over here, if we take negative 1 times by I, we should get negative I. So we get these imaginary axes, which is just in a whole nother plane. It's not a real number. Can't exist over here. Has to exist, right? It can't exist over here. It has to exist on this axis. Okay? Lovely. Okay, got that out of the way. Let's just think about now, so that's kind of the intuitive approach why we say it's 90 degrees. And there's another explanation we can use, and we can use Euler's identity. But before we get to Euler's identity, I just want to take the time to create another identity, which is now, if we've got two number systems that are entirely separate, we normally call a complex number z. I put a little line through it because I confuse my z's with 2's. And then that's equal to x plus iy. Okay, x and y, I'll tell you why we choose that in a minute. But that's how we choose it, okay? So here, x, if I take the real part of z, think about the real part as just being a function. Okay, I take some complex number, or in fact a real number, and it just takes this form and it says, okay, you know what? Let's take this one. Okay, I want the real one. I don't want nothing to do with I get that out of the way, and I'm just going to focus on that x part. And that should give me x in this case, okay, if it's in this form. And what about if I take im of z? Now you can imagine, well, we're just taking the imaginary part, right? That makes sense. Let me convert this to maybe blue. So we're just thinking about this part here. Okay, we're not talking about y, okay? I want you to keep in mind, even though we're talking about the imaginary part, we don't care about I. We're talking about the part, not I, okay? So both of these should give real outputs, okay? Just one thing to make clear. Okay, I is just sort of the imaginary thing. Okay, it's just an imaginary part, but we're always going to be timesing I by a real number. Okay, lovely. We got that out of the way. Let's right. Let's plot. So we can plot these numbers here, x plus I y, on the number line, or on the Argand diagram. Sorry, should I say? So here, that part should be x because that's the real part. Like we said, the real part is equal to x, and then here should be y, right? Because the imaginary part is y, and I should probably say iy to be more specific. But there we go. And that's the reason we choose y and x, because it's like the x-axis and the y-axis, right? And now what we do the similar thing we do with vectors. We draw a little line from the origin. Okay, just how we do complex numbers. You don't need to, but it's very useful to do so. Okay, it's very useful. Just think about sort of like a line, like a polar coordinates, if you've done polar coordinates, or like vectors, for example. Okay, lovely. And what we're going to think about is we're going to think of another a few more things. So the first thing here is the distance. Okay, we call the modulus. It's absolute value. In many ways, we use this notation. So z, and you put a little mod sign like that. Okay, so that's what we say. We say mod z, and that's just the distance. And you can imagine if it's a distance, what we're doing from the origin, we're just simply doing Pythagoras, doing x squared plus y squared, and then square rooting it. So we can just say this is equal to x squared plus y squared, like so. And I'll highlight this because it's pretty important. Oh, sorry, wrong thing. My bad. There we go. Okay, lovely. That's the modulus. That's what we call the modulus. I mean, I don't know, maybe people call it different words. I call it the modulus. But yeah. Or I think people say, what is it? There's many names for it. Absolute value, maybe some people call it. I don't know, but I call it the modulus. Okay, and then here, this is theta, and that's what we'll be focusing on later, or soon. That's what we call the the argument. There we go. That's called the argument. Okay. So we normally say theta, well, that's equal to arg of z, which again is just another function. It's just saying, okay, well, take take the angle that's between the positive real axis and the actual line, and we represent this as being arctan. Okay, and you can just use simple trigonometry here of y over x, and keep in mind we can use here. We know y is the imaginary and x is the real part, so we can say this is im of z and real of z. Lovely. And let's highlight that as well because it's important. Just one more thing about the modulus I forgot to say is that we also call it r. Okay, r kind of means like, I think, radius, because it does have something to do with radii. We'll get to that in a minute, but yeah. Okay, now let's get to our little derivation. We can call that r. Well, this here, you can just use some trigonometry, must be z, or mod z, multiplied by sine of theta. And this part here must be mod z cosine of theta. And we're just using trigonometry. Sine of theta is opposite over hypotenuse. So hopefully, if you're doing complex numbers, I'm sure you should be pretty comfortable with some trigonometry. Because this is, in fact, a right-angled triangle. Okay. And there we go. That's that. Okay. You could also say, because of our symbols, we might say r sine theta, and we might call this r cosine theta. Okay. So there we go. And we can say, right, that this is equivalent to y. And this is also equivalent to x. And that's really important. Okay, that's another thing I'm going to highlight. Okay, that's really important. If that's the case, then we can write, if we write z equal to x plus iy, well, we can also just say that z is equal to, well, x, which is r cosine theta, plus, and then I, and then we're taking out y over here, so I'm kind of going to highlight these guys. Y, which is r sine theta. So I, r sine theta. And then there we go, we're pretty much done. We've got r in common, so we can just take out r. And we call that cosine theta plus I sine theta. Or, depending on the notation you want to use, you can say mod z, and then cosine of theta plus I sine theta. It's up to you what you want to use, but the point is, this is important. Okay, and that's kind of where we got the complex number thing from, right? And if you know Euler's identity, which we did prove in the other video, e to the I theta is equal to cosine theta plus I sine theta, which means that we can represent any complex number, z, okay, just by making this little simple substitution as, well, r, right here, times by the rest, which is e to the I theta. Isn't that nice? Okay. So I'm just going to draw another Argand diagram because this one's kind of busy. So here it is. Yeah. So yeah, this is again important. If we draw another Argand diagram, thinking about a modulus r, and we're thinking about an angle theta, if I think, and this is z, if I allow z to vary over points, well, what you're going to get is you're just going to get a circle. A really badly drawn one, but you'll get a circle. And I should probably say this is the real axis, and this is the imaginary axis. But yeah, if you allow z to vary, or should I say theta to vary, okay, so here's what happens if you allow theta to vary. To vary. Then this is the output z gives. Z gives a circle as an output. So this is sort of like a complex function, okay, in a way, and it gives a circle. So isn't that pretty cool? Yeah. So yeah, maybe I'll do some more on Argand diagrams because you can plot different things on Argand diagrams. You can plot a circle a bit differently using Argand diagrams. You can move the center, but it's nice to think about it as exponential. And really, there's no explanation. Like I said, I don't really think this is the best I can really do. Is think about, well, that's that. Okay, you can represent it with trigonometry, but you can also represent that trigonometry with this. Okay. With this little, with e to the power of something, just because the series work and the maths works. Okay, that's the proof for it. It just kind of works. It's probably how nature works. So yes, thank you so much for watching this video if you made it this far. I hope this is a decent explanation. I'll try to do more on Argand diagrams because they're quite interesting. Yeah, so I'll see you in the next one.